Hi, hope you're doing well. Today we are going to talk about the perceptron. So the perceptron is one of the earliest deep learning algorithms. Well, I won't call it a deep learning algorithm because it is trying to mimic a single neuron in the human brain and it has only one layer. So it's not really deep, but it kind of paved the way towards modern deep learning. So perceptron made multi-layer perceptrons or feed-forward networks possible, and that's where deep learning started. So perceptron was developed in the early 1950s, and this is what Frank Rosenblatt had to say about it, the inventor of perceptron. So we can see that this is quite an exaggeration and things did not turn out like this. We will understand why in the later lectures, but yeah, this is a picture for you to see of the Mark I perceptron, which was developed as an hardware equipment. So since perceptron was developed in 1950s, why did it take so long for deep learning to really thrive? Well, before we talk about that, let's talk a little bit about machine learning and how is deep learning a bit different from machine learning. So you can see this example here. This is one of the very famous examples. Most people getting started with machine learning start with this example. It is called the iris dataset. So in the iris dataset, what researchers have done is they have manually collected these samples of iris flowers, and to differentiate them, what they have done is they have manually chosen the features. So you can see the pictures here. All these different species of iris kind of have a different look, and we can see that the length of their petals and sepals are different in each one of them. So the scientists took these as features and created this data set. So you can see the features are being chosen manually and they are being collected manually, and we are trying to train a model upon them. So in traditional machine learning, humans need to choose the features on which to train the model. It is A, time consuming, and 2 is brittle because it kind of inculcates human error as well. So since it is time consuming and it is brittle and prone to human error, it is not very scalable. Now this brings us to a question that what if our models could learn and find out what features to adapt to and find this pattern from the data itself. So we can give our model a large data set and it can figure out what features to focus on and what patterns to detect. Now this would be possible if we have a large data set to train on, which was not the case in before like the internet revolution. Now you can see that I have attached a screenshot from Hugging Face, and in the fine web dataset there are more than 25 billion rows, and this was not possible before the internet came along. So imagine the kind of compute you would need in the 1950s, 60s or even 80s to train on such dataset. So to train on such dataset, we would need lots of compute, as well as we need to parallelize the training process. So all these things were not present earlier, and now we have them. Now we have GPUs to do the parallel processing, and we have libraries like CUDA to write instructions for those GPUs. And we also have autograd libraries like PyTorch and JAX, which are open source and really useful and make it really easier for us to implement deep learning algorithms. So let's now that we know how machine learning and deep learning are a bit different, Let's start with the perceptron model. So this is what the architecture of a perceptron model looks like. In a perceptron, you have multiple inputs. You can have as many as you want, and each input layer has a weight associated with it. Now, what we try to calculate is the weighted sum here. So the weighted sum means each one of these inputs will be multiplied with their respective weight, and the sum of all those products will be calculated. This is what the first node here does, and once the sum is calculated, it is passed along through an activation function to get the output y hat. Why y hat? Because this is the prediction of the model. The actual result that we provide in the training data set would be y, and y hat is the predicted value by the perceptron. So in this lecture, we are going to focus on this process. It is called the forward propagation or forward pass. In the next lecture, we will see how a perceptron model is trained and how the backward pass comes in. That's where y would come along, and we would see how we can nudge the model to learn the real y instead of producing this y hat. But let's stick to the forward pass for now. So this is what the perceptron looks like, but I'm missing something here. Actually, there is also another term called the bias term. Now this bias term is represented as W0, and we multiply it with 1. So any number multiplied with 1 is the number itself, right? So we add this bias term in our equation, and now if you see, then the equation of the perceptron kind of looks like the equation of an hyperplane. So hyperplane is like a line in multiple dimensions. So stretch a line into multiple dimensions. In 2 dimension, it is a straight line. In 3 dimension, it becomes a plane, and in dimensions beyond that, we can call it a hyperplane. So inherently, perceptrons are linear until this part. That's where we add a non-linear activation function to it. Now I'm talking a lot about activation functions. Let's see what these activation functions look like. Oh wait, before that I need to discuss one more thing. So you can see that we are doing the summation here, and how would you do a summation in a program for multiple values like this? The first thing that would come into mind is running a for loop, but we know that for loops are really not very efficient, and we want our algorithms to be very efficient because we are training on large data sets, and the more efficient our algorithms are, the cheaper they would be, and the faster their training time would also be. So we can see that the thing that we are doing here, which is calculating the weighted sum, can be replaced with a dot product. So in dot product of 2 vectors, you do a similar thing. You kind of take the transpose of one of the vectors and you multiply it with so you multiply a row vector and a column vector such that you multiply the values in the same indices of both of these vector, and then you sum all those products. So when we replace it with a dot product and vector algebra, it is possible to parallelize these things. So what you can do is you can run each of these multiplication operations in different cores of GPU using CUDA, and then you can parallelize this process to make these calculations really fast if you have a high compute. Now let's talk about the activation function like we discussed. So This is what a typical activation function would look like. Here I've taken example of the sigmoid function. So what this sigmoid function does is, if you see, it has a special characteristic which is it will always squish the value between 0 and 1 no matter how high the input value is. Now because of this, we are sure that okay, we are not our values are not exploding into really large numbers that are difficult to compute, and the value is always between 0 and 1. And also it adds a non-linearity to it. If you see the cursor here, it is following the non-linearity in the graph. Now we'll see why that is important, but before that, let's also talk about a few more of the activation functions. So some of the other common activation functions are tanh and ReLU function. So the hyperbolic tangent function looks very similar to sigmoid. The only difference is that it stretches from -1 to 1. Sigmoid here stretches from 0 to 1, and this stretches from -1 to 1. And then we have the ReLU, which is a very simple function. So ReLU, what it does is, if the number is below 0, so if it is a negative number, it would return 0. Otherwise, if the number is a positive integer, it would return the integer itself. So a special thing to note here, do not get confused by the absolute function. Absolute function would return the positive value of the number no matter if it is negative or positive. But ReLU here, what it will do is, it will nullify the negative values and only give you the positive values. Now in a typical neural network, what you will do is, you will not use just a single activation function. You will kind of mix and match these functions in the different layer to model on your data set. Now how do these functions help in modeling on a data set is like this. So imagine this is what your data set looks like. Well, this is a very simple data set that we have taken. Real life data set can get a lot more complicated than this. Now if you remember the perceptron algorithm, let's forget this for now. So we know that this is the equation of a straight line. Let's try to model our data set through that equation itself. So here you can see, no matter how we draw a straight line here, this data set is not it cannot be modeled by using a straight line. So straight line would not capture the essence of this data set, no matter how many layers you add into your network. If there is no activation function, the network would always try to fit it using a straight line, which is really not possible for this data set. So which is why we need activation functions to add non-linearity to our data set. Now activation functions, what they do is, we know that we can see that none of the activation functions that we mentioned here are linear. So when our input is passed through this activation functions, a bit of non-linearity is added. So what we typically do is, we create layers of these perceptrons, and we use multiple of these perceptrons as single nodes and create a neural network and train our model on that. So what happens, these little activation functions are superimposed, because of which even a complex non-linearity like this can be captured. So that was all about the forward pass. Let's do a brief revision of it. So in a perceptron, you have inputs and you have a bias. All of these inputs have respective weights. You multiply each of the input with a weight, calculate the sum, and pass along to an activation function for non-linearity. to get the value of y hat. This, in simple terms, is known as the forward propagation. Now, in the next lecture, we will talk how to train a perceptron, what are loss functions, what is gradient descent. We'll learn backpropagation, and we'll also see how we can use this perceptron for regression and for classification. We kind of saw the classification example here, but we will implement it by using NumPy or PyTorch. Okay, so see you in the next lecture.